whether the charge on an object is expressed in millicoulombs, microcoulombs, or nanocoulombs, or even picocoulombs. Regardless, somehow that object must have had those charges transferred from one place to another. So we say there are a couple different methods of charging. The one in which charge is transferred from one object to another can be referred to as charge by conduction, which could be a result of charge by friction. These two are roughly the same thing. The familiar case of charge by friction is walking across carpet and your socks interact with the fibers of the carpet, and electrons, we'll say, are stripped away from the carpet and end up on your socks and therefore on your body. And then when you go to touch the doorknob, those very same electrons can then transfer from your body back into the doorknob and ultimately back into the ground where they came from originally. Okay, so in this method called charge by conduction, there's a few things to keep in mind. One, in charging by conduction, electrons are transferred from one object that we'll call A onto another one that we call B. So in this example, we could say the carpet is object A, and your body or your socks are object B. So this means that object A, the carpet, is now positively charged because it's lacking in electrons, and your body is now negatively charged because it has the excess electrons. And note that in this process, the charge was not created out of thin air, so to speak. Charge is never created or destroyed. There's a law of conservation of charge that governs this process. So there you have it. One method of charging is charge by conduction. Friction doesn't have to be the result of your feet rubbing across carpet. We get a similar process to charging by friction in the updrafts and downdrafts within large cumulus clouds. So in that process of the air just rubbing past one another, right? As these molecules swipe past each other, there can be a transfer of valence electrons, and the result can be an accumulation of negative charge in the bottom portion and positive charge. In other words, the ions that are left behind in the upper portion, right? It's not so much that they've gained protons, it's just the nuclei stay the same, but there aren't as many electrons in orbit around the atom, so you're left with positive charges in the top. And the lightning strikes that result, sometimes you just see the flash in the sky. It could be because charge is transferred from one cloud to another, or often the whole cloud will light up as the charges are redistributed and it's neutralized due to a lightning strike internal to the cloud. And then often the more impressive cases are where we see the discharge between the cloud and the Earth itself. Another process of charge by conduction can be seen in the operation of the Graaff Generator. So in the Graaff Generator, again, charges are conveyed from one place to another. So this is ultimately attached to the ground by way of the plug that goes into the wall. And so electrons are transferred by this conveyor belt bringing electrons from the bottom, carried up to the top, and then deposited all around the surface of the Van de Graaff. So that means the ground itself is lacking in these electrons, and a transfer of charge from one object to another is taking place, charge by conduction. So what's the other method of charging? Well, that's known as charge by induction, which could be a result of charge by polarization. And I'll give you a couple examples. Okay, so just to be clear, if you were to bring a object that had previously been charged by conduction, let's say this is a plastic or a glass rod that has a lack of electrons, so the object is positively charged. If you bring it near a conductor, a neutral metal sphere, then that sphere will become polarized. The free electrons will have an affinity to the positively charged rod, and therefore those free electrons will flow across the surface and accumulate on the left side of the sphere, leaving you with positive charge on the right side of the sphere. So there's a dividing line, right? The left side is negative, the right side is positive, and we now say that the sphere is charged by polarization. If something has been charged by polarization, it's very different than charged by conduction because it doesn't lead to any net charge on an object. The whole sphere in total is still neutral. All it's really done is, it's polarized it. It's created a portion that's negative and another portion within it that's positive. So what we can do is put two metal spheres together. They're both originally neutral, but they're touching each other. They're in contact here. And we can charge that whole system by polarization. And so the free electrons will go across the outer surface and accumulate on the left sphere, leaving the right sphere positively charged, as indicated in this second diagram. So the system is now charged by polarization, and then if you grab them with your hand and pull in opposite directions to separate these two, now each of them has a net amount of charge. So not only was the system charged by polarization, but when you separate the two, now this whole system has been charged by induction. Let me give you some other examples of charging by induction and conduction. This example you might have seen in another video or in class. It's known as the Electrophorus. There's a metal plate with a plastic or wood handle. Okay, so the plate is a conductor and the handle is an insulator. And then there's a acrylic base. Acrylic's like plastic or plexiglass. It's an insulator. So the process goes something like this. With your hand, while your feet are touching the ground, boink, you touch the metal plate. Okay, well, in doing so, that guarantees that the metal plate does not carry any net charge whatsoever. If somehow it had excess electrons on it, then in that moment that you touched it, those electrons would conduct through your body and into the ground. If the plate somehow were lacking in electrons, then when you touched it, electrons would flow up through your feet, through your body, and from your fingertips into the plate to neutralize it. So basically, touching it makes sure that it's been neutralized. And so that's how we start the process with the Electrophorus. Now, you can grab it by the handle. Let me clean this up a little bit. And first of all, note that if we were to zoom in on a small region of this plate, we would expect that there'd be both positive and negative charges in the nucleus of the atoms, negative charges here represented by some of the free electrons that aren't bound to any particular nucleus, and there should be an equal amount of positive and negative charge if we say the plate is neutral. Now, if we were to rub the acrylic base with some fur, then we can transfer electrons off of the fur and onto the acrylic. So in that part of the Electrophorus, charging by conduction takes place. The base overall is negatively charged if electrons were transferred off of the fur and onto the acrylic. So that's what we'll assume in this case, that the base overall has a negative charge to it. So we grab hold of the handle and move the metal plate close to this base, and then this changes. No longer are the positive and negative charges randomly distributed. The electrons will want to move to the upper surface, leaving you with positive charge on the bottom surface of the plate. Okay. So if that's the case, and now you lift it back away, then the distribution of positive and negative charge is back to random. So with the metal plate far from the acrylic, random distribution of charge. When the plate is held close to the acrylic base, there's a polarized distribution of charge. So if you were to grab the metal plate by the handle and bring it near an electroscope, we wouldn't expect anything to happen. After all, the metal plate is still neutral, and so there's no interaction with the leaves of this gold leaf electroscope. Okay, however, we can take advantage of charge by induction if the metal plate of the electrophorus is held close to the acrylic base such that it's now charged by polarization. And at that moment, again, you touch the plate, then the electrons don't just want to accumulate across the top surface of the plate. The electrons actually want to travel through your hand and through your body and into the ground. So now this metal plate is positively charged. And if you take it and move it near the electroscope, because the plate is now lacking in electrons due to the fact that they've conducted through your body into the ground, then all of the electrons in the electroscope respond. They have an affinity for the plate, and so electrons vacate this piece of gold foil and go rushing toward the top, and they also vacate this piece. So basically, the electroscope is now charged by polarization. Electrons come to the top, leaving you with positive charge in both of the gold leaves, and then the two positive charged leaves repel one another and spread apart, and so you can identify that there is indeed a charge by induction that resulted on the metal plate of the electrophorus. At that point, if you pull the plate away, touch it again, now the electrons can come from the earth and flow back through your fingertip and back into the metal plate and neutralize it once more. So the electrophorus gives us an example of both charge by conduction and charge by induction. One last example that I'd encourage you to try on your own at home. Get an empty soda can, an empty aluminum can, and if you have one, take a balloon and rub it in your hair. It would also work if you took a big plastic comb and rubbed it in a wool sweater. Rub anything made of plastic with anything made of some sort of natural fiber, and you'll get some charging by conduction that takes place. So let's say in that process of charging the balloon by conduction that you have stripped electrons off of the balloon and onto your hair. In that case, the balloon would be positively charged if it's lacking in electrons, but the comb is neutral. The can is neutral. Now we take the balloon and move it toward the can. Okay, well, if we draw a better picture of this can, maybe zoom in on it. What happens is the can gets charged by polarization as long as the charged balloon is close to it. And you can imagine in which direction the electrons go. Free electrons in the metal can have an affinity for the balloon, so they go to the right side. And that means the left side has a positive charge to it, right? So the can is charged by polarization. Okay, well, that leads to a force of attraction because this half of the can is attracted toward the positively charged balloon. Now you might say, wait a minute, there shouldn't be any net force at all because after all, the left side is going to be repelled by the balloon. However, distance plays a role in the magnitude of the force. The distance between the right side of the can and the balloon is shorter than the distance between the left side of the balloon, and so it turns out my force diagram isn't quite right. The force of attraction is going to be greater in magnitude than the repulsion, and so overall there's a net force directed to the right. And what you'll see in this demonstration, if you try it at home, it works every time. When you hold the balloon close to the neutral can, the can will start to roll and go towards the balloon. Okay, so I encourage you to try that one for yourself and see if you can bring this physics to life. Anyway, for now, thanks for watching.